right, so let's go ahead with this 12.6. Calculus of vectored valued functions. So calculus of vectored value functions, really not any big deal. Really, you're what you think is going to happen is what's going to happen. So let's look at this definition to start us off. So our definition is on page 805. If you're looking at your actual textbook, or it's the definition in 12.6, we're going to let R of t equal f of t I plus g of t j plus h of t k, where f, g, and h are differentiable functions on the interval from a to b. Then R, so my vector R, has a derivative on a to b, and here's the deal. The derivative of R of t, so R prime of t here, is simply f prime of t I plus g prime of t j plus h prime of t k, provided that the derivative does not equal 0 and R prime of t is a tangent vector at the point corresponding to R of t. So let's talk about what is obvious here. If I have this, we're going to let my actual just vectored value function, remember you can write it in terms of ijk, or you can write it in those triangle brackets. It means the exact same thing, where each one of those functions are differentiable on a specific interval. Then the derivative is just the derivative of each piece. That's it. You're just taking the derivative of each piece. And what is the derivative? It's slope of the tangent line, right? So this derivative is the tangent vector at some corresponding point. So it is the tangent. The same thing that's happening here. So this is not, we're not doing anything super crazy. We're just going with this. So here's example 1. Find the derivative. If, for part A, I have my vector here of t, and that's t cubed, 3t squared, and t cubed divided by 6. My derivative of this vector is going to be 3t squared, 6t, and if I bring that 3 in front, so 3/6 will give me that 1/2 t squared, or t squared over 2. Literally, that's it. How sweet is this? Pretty cool, huh? Let's do more. What if I want to take the derivative of this? E to the negative ti plus 10 square roots of tj plus 2, that's a 2. Try it again. 2 cosine of 3tk. Let's get this up. We're just simply going to take this derivative. So R prime of t is now negative e to the negative ti. So this is the same thing as t to the 1/2. So if I bring the 1/2 in front, that gives me 5t to the negative 1/2 j. Now if I have, well, it's going to be negative, right? Because the derivative of cosine is negative sine. So I'm going to have a negative because of my inside function here of 3t. That's going to give me this 6 sine of 3t. Okay. Da-da-da-da-da-da. Awesome. Pretty sweet, isn't it? Oh, I love it when a plan comes together. Okay. Not too shabby. So we can also have a unit vector. So on page 806, there is a unit tangent vector. And we know tangent just means derivative. So if I am given my vector, my vector valued functions here, r of t is still f of t, plus g of t plus h of t. A unit tangent vector of length 1, because that's a unit, right? That's the whole point. Is this t of t, just to show that it's a unit tangent. So that's what the t is the derivative of my vector t over the magnitude of my derivative. So just like a regular unit vector, where it's just my vector over the magnitude of my vector, this is just the tangent one is the derivative. So it's the derivative over the magnitude of the derivative. Okay, so let's do one. Keep that formula up there so we can still see it. If I want to, we're going to do example 2b. Find the unit tangent vector. Of this 10, 3 cosine t, 3 sine of t, 4, 0, which is less than or equal to t, which is less than or equal to that 2 pi. 2 pi. So if I want to find the unit tangent vector, I need to find the derivative and then the magnitude of said derivative. So first thing we need to do is find that derivative. So the derivative of 10 is 0. The derivative of 3 cosine of t is negative 3 sine of t. The derivative of 3 sine of t is 3 cosine of t. So there's our derivative. Then we find the magnitude. And so then my magnitude is going to be 0 squared plus negative 3 sine of t squared plus 3 cosine of t squared. Then simplify. So 0 is just 0. So this is 9 sine squared of t plus 9 cosine squared of t. And then we get to use a little bit of trig knowledge, right? So we can simplify this a little bit, factor out that 9, and I'm left with sine squared of t plus cosine squared of t. And we know, because our fancy pants Pythag identity, that's going to give us a 1. We have the square root of 9, which is 3. So if I'm looking for my unit tangent vector, that is going to be r prime of t divided by the magnitude of that derivative. So I get 0, negative 3 sine of t, and 3 cosine of t over 3. We do a little division, and we end up with 0, negative sine of t, cosine t. There is our unit tangent vector. Pretty sweetness. Cool. Cool. That's it. So we're not, this one with finding the derivative, the beauty of finding the derivative, it's not like we're recreating the wheel here. It's stuff that we already know about and we just go with. So all of the derivative rules that we have, again, we just go with it. Whenever I'm looking at these different derivatives, we just use the exact same rules. So the derivative of a constant is 0. You will add those up, you take the derivative of each piece. You do the product rule whenever you're taking a function times a unit. All of these things happen. A few of the derivative rules to go with what we know about. What if I want to take the derivative with respect to t of the unit vector, the u vector dot, oopsie daisy, dot v, right? So now we know the dot product and the cross product, and we can still take the derivatives of those. Whenever you do the dot product, it looks just like the product rule. Or if I'm going to take the derivative of my first times the second, dot the second, plus the first dot the second. So you're just dot producting that, right? Same thing. So it's like the product rule, and so whenever you dot product, right, you're finding the dot product of these two vectors to get that scalar value, you find it this way, then you can dot those two values. Same thing happens with cross products. If I want to take the derivative with respect to t of u vector cross with v vector, then you get u prime of t cross with v of t, because the derivative of the first times the second, plus the first times, in this instance it'll be a cross because the cross product is the operation that we're using here, the derivative of the second. So it's the setup is the same as the product rule. It's just what operation are you doing. If you start with the dot product, then you go with the dot product. If you start with the cross product, then you cross those two as you go through there. One thing I will say is that the order matters. So make sure you take care of that because you're crossing these values. So the order definitely matters whenever you're doing that cross product. Okay. So let's do this thing. Let's do this example.